In this video, I want to talk about some different applications for nodes and networks of nodes. Programs are usually written into text files, but they can also be created by connecting logic nodes. And that can have advantages and disadvantages, and hopefully I'll get around to talking about that in another video, as well as geometry nodes used in newer versions of Blender. For now, I'm going to show a simple example of how a network of nodes can be used to test if two math expressions are equal. So a network of nodes can be represented by a mesh in Blender. And here I have an arbitrary mesh, and if each of these vertices were to represent a math expression, then expressions that are equal would be connected and expressions that are not equal would be separate. However, you could connect all expressions together using conversion nodes, but you'd want them to be visually distinct. So if this node were to be, say, expression A, and I wanted to know if that were equal to some expression E, then you can see that they're equal because there's a path between them. A would be equal to B, B equal to C, C equal to D, and D equal to E. And the path gives the conversion, the way to convert between the two expressions. Expressions by unconnected vertices are not equal. I've written a script that demonstrates a simple example, so I'll show that. So here in this expression variable, I have these two sides of this equality that I want to check, and both sides of this equation are equal to 1. So if I run this script, it will make a map of how these two expressions are connected. So in older versions of Blender, I can select a vertex by right-clicking, and then if I control and right-click on another vertex, that will give a path between the two, and that represents the conversion. And the map doesn't show how this expression is equal to 1. And that's because I've manually entered it into this database. So here in my database, I have identities and equalities. Identities are true for any variable or value, and equalities are true for specific values or specific expressions. So here's this entry that I put in manually, and if you want to know a little bit more about exactly why that's equal to 1, it's because e to the I theta draws a circle in the complex plane. This is equal to cosine of theta plus I sine of theta. So if you plug in pi here, you get sine of pi is 0, the imaginary term goes away. Cosine of pi is -1, and if you negate that again, you get +1. And my script is not yet smart enough to connect functions and to make those conversions. Also, psi psi is equal to root of 5 minus 1 over 2. And that's actually the only entry I need, but I've added these other entries because the script doesn't perform computations. It's basically a parser. It parses expressions, makes the conversions listed in this identities file, and then makes comparisons, checks for the equalities equal to here. So here this division operator is a shortcut for 1 over a. So this is 1 over a times a is equal to 1. This is 1 over a to the power of b is equal to a to the power of minus b. And the reason I'm doing that way is because of order of operations. For example, a minus b is not equal to b minus a. That's because another way to write this is a plus minus b. And this could be thought of as b plus minus a, and here the negation is associated with the opposite variable. But if you write it like this and reverse the order, then it's still true, so that makes the code a lot simpler. The same is true with say you have 2 divided by 5 is not equal to 5 divided by 2, but you could rewrite this as 2 times 1 over 5, and that is equal to 1 over 5 times 2. So in the script there are basically 3 operators. There's the exponent operator, the multiply operator, and the add operator. The minus and divide symbols are being associated with variables. They're basically negations. The minus variable is a one-dimensional negation, and the divide symbol is a two-dimensional negation. And double negations work the same way. So a minus minus is a positive, and divide or 1 over x is just equal to x. So a double negation is just ignoring. So that's basically it, and that's the general idea. There's also a game script that allows these nodes to kind of be click and dragged around. And I haven't yet written a function that kind of untangles these nodes. The way I did the example that I showed previously is just by manually storing these vertex locations here. So you don't actually need a computer to do this. Another way you could do a similar thing is by making, say, a deck of cards, each with an expression on them, and then you could rearrange the cards and try to connect two expressions together that way. And in the future I'll talk about programming using logic nodes, and rather than thinking about a program as a collection of nodes, you can think about a program as being a path through a network of all logic nodes, and that's true for geometry nodes as well. And node networks don't necessarily have to have anything to do with technology. One project I'm working on is generating a map of how ingredients combine to make different recipes, and that can be used to make new recipes. So going back to the script, the first function called is node, and there are three main functions that node uses to work. The first is expression parse here, the next is join here, and the third is convert. So what expression parse does is breaks a string into a list. So for example, this first expression here can be separated into smaller pieces. This piece inside this exponent here is the same as this piece. So what I could do with this is, well, first of all, I could add this add. So I look for this add operator and split this into two pieces at that point. So I could call this index 0 and add this piece to a list. So psi to the 1 over psi times 1 over psi to psi, and that's actually equal to psi. So this is kind of a convoluted way of writing psi squared plus psi equals 1. So here's the 0th entry in the list. Next I could add this part. So psi to the 1 over psi times 1 over psi to psi. And then I can convert this into at 0 plus at 1. And then I could continually, to separate these, I could add this 2 into a new entry, add this into a new entry, and then rewrite this expression as at 3 to at 2. And I'll show that in the program. So here, expression 0 is equal to this. So if I update this with expression parse, then I put that string into a list. So here's that list. Join rejoins an expression into a string. So if I wanted to join the 0th index of that list into a string, then I pass the 0th entry. This expression 0 is now a list. It's this list. And then I also pass the list as well. And then if I print that, I get back my original string. I can also print, or I can join a different piece. So if I pass like 13 instead of 0, then I'm joining this 13th entry, and here's the 3rd index and the 4th index, so I'll get this. And that's how I check the identities file for rules like this. Or, sorry, not that one, this one. So using this, that can be converted to psi to the power of minus psi. And that's the first step in this conversion. This piece here becomes psi to the minus psi. Same with this piece. And that gives these two variables a common base there and there. And that allows this identity to take effect. That converts that to this. Then in the equalities file, 1 over psi plus minus psi is equal to 1. That allows that to take effect. That converts this expression to this one, which is converted into this, which is, that check is made there, that converts it to 1, and that connects it to that expression. So I'll show this expression parse function, put that back to how it was, and show this node function. So here's expression parse that breaks a string into a list. The first thing that this function does is look for parentheses and separates the parenthetic expressions into their own index. The next thing that's done is variables are added to their own index. Then expressions are separated until each index in the list only has one operator, and that allows for simple rules to be written for making conversions. And next are the functions that expression parse relies on. Join rejoins the list of indices into a string, and these are the functions that join relies on. Convert checks if an expression is able to be converted by an identity and if it is, it makes the conversion. And there are certainly errors I haven't found, but this is a project that has a lot of work left to do. Here's where these double negations are canceled. Next are the functions that convert relies on. Next are the node functions. Write and read are for connection lists, which are like edge lists in Blender, except they're much larger. But the trade-off is that they're faster to purge or copy connections to different nodes. This list shows how a single edge is connected in Blender. This says that the 0th vertex in the vertex list is connected to the first vertex in the vertex list. This has some redundant information. This says this is a list of nodes that the 0th node is connected to. So it's connected to the first node, like in this example. And the first node is connected to the 0th node, because this is the 0th entry in the list for the first node. And that allows connections to be looked up from either list. So you can find the connection in entry 0, as well as the connection back to 0 in the first entry, or the first list. Then there are the general functions that are used throughout the script. And lastly, I'll show my library functions, because sometimes I update those, and that can break functionality with old programs. So the module file is used for custom Python libraries, and this is the central location that kind of links all the different scripts together. Then I'll show the functions used in the Python library, which are basically general functions. There's the file to lines functions, which converts a file to a string list. The exist function checks if an item exists in a list and optionally returns the index. White removes white space from a string. Next is the Blender library. Name renames an object. Pad converts an integer to a string with a width of 3 characters. Select selects an object. Origin to cursor sets an object's origin to the location of the 3D cursor. Cursor sets the location of the 3D cursor. Location sets the location of an object. Next is the Blender game library. Mouse sets the option to show the mouse cursor in the game. Frame extend removes the black space from the top and bottom of the window. Logic sensor option returns a dictionary of sensor options to be passed to the logic function. Logic sensor dictionary returns a dictionary of sensor parameters. logic controller dictionary returns a dictionary of controller parameters. Actuator returns a dictionary of actuator parameters. And then those values can be set in those dictionaries, and then those dictionaries are passed to the logic function. And the logic function adds logic bricks to an object, as well as does some other things like linking and loading script files and loading things like sound files. Properties function adds blender properties to an object. And lastly, I'll show the game script that's loaded onto the camera, which draws lines between the nodes, allows the nodes to be clicked and dragged, and controls the camera. So just wrapping up, I'll say that I used to think of math proofs as a step-by-step process, and if you're making them from scratch, they are. But if you accumulate a large enough network of expressions, all you need is an entry and an exit node. If there's no path, then either the expressions aren't equal or you don't have enough nodes. And that same idea applies to other problems as well. And that's the end of the video, so thanks for watching, and see you in the next